All right, very good morning. Let's go ahead and get started. Now, if you can hear me, I want you to start by raising your hand. Okay, good. So we'll continue. Thank you. You can lower your hand now. We'll continue from where we left off in the last class, which is talking about dependent and independent sources. But before we do that, let's quickly see what we did in the last class. Okay, what we did was to begin with the idea of basic ideal circuit element. Okay, basic circuit element, it's symbol, how wires are connected, what it means to be a connected and not connected wired, so crossover, so on and so forth. Then we looked at the basic circuit elements: capacitance, resistance, inductance. And in addition to that, I mentioned there is independent voltage and current sources, right? It is independent voltage and current sources. And in addition to that, so this is a voltage source, this is a current source. In addition to that, there can be any number of 4 types of actually dependent current sources or dependent voltage sources, dependent sources. Okay, so there can be a voltage or a current source. So these are the circuit elements that we encounter and that we spend time with most of the time in this class. Okay, then we talked about the idea of passive sign convention. Okay, passive sign convention is something that we follow as a standard, a rule that we set for ourselves in order to be consistent throughout the circuit. Okay, so it is an arbitrary choice in the sense that if we do the exact opposite and be consistent with that, that will lead us to the right answer as well. So the choice is kind of arbitrary, but because we chose it as a standard, we like to stick to it. The idea is, the standard is this: if the current is flowing in the direction of the voltage drop, so if the voltage drop is bottom to top, there is a bigger voltage here and a lower voltage there. So the voltage is dropping along that direction. And let's say the current is also flowing in this direction, shown as I. Then we consider it to be a positive current. Okay, so current in the direction of voltage drop is positive. The opposite is negative. Okay, current against the voltage drop is negative. Okay, that's the sign convention we followed. And we also define the terms power and energy as it applies to electrical engineering. Okay, we define the terms power and energy. Power is simply V times I. The a particular circuit element could be delivering power or absorbing power. Okay, that's something we looked at. When is the circuit element absorbing power? When the product of V and I is positive, then the circuit element is absorbing power. Okay, and when the product of voltage and current VI is negative, then we say the circuit is delivering power. Okay, this is something we looked at in the last class. Okay, so we looked at different examples of when a system is absorbing power or delivering power. Sometimes the same circuit element could be doing 2 different things at 2 different times. Okay, like a battery could be absorbing power when it is charging, and it could be delivering power when it is lighting up a screen. Okay, and then I showed the relationship between between the power and the current, okay? Current and the time it takes to charge a battery, okay? If I'm using a bigger current, it takes a smaller time to charge the battery. If I'm using a really small current, it takes a lot longer time to charge the battery. That's the idea, okay? So this is what we did in chapter 1 in the last class. We didn't stop there. We went on to chapter 2. Chapter 2 is circuit elements. And when it comes to circuit elements, we started looking at voltage and current sources. Okay. We started with independent current sources, and then we went on to dependent current sources. Okay. A voltage source is a circuit component whose voltage is set. So independent of this value, even if the RL value is changing quite a bit, up or down, the load value, the external circuit, even if that is changing, this guy is set. The voltage across the voltage source is set. The current could be different, okay? The current could be varying, okay? But what is constant is the voltage across a voltage source that is set. Similarly, the current coming out of a current source, that guy is set. Okay, all of this we discussed in the last class. Okay, so we looked at current sources and voltage sources, and then we went into the idea of dependent current sources. Dependent current sources. Okay, there can be 4 types of current sources. Voltage dependent sources. There can be 4 types of sources: voltage controlled voltage source, current controlled voltage source. There can be a voltage controlled current source and current controlled current source. Okay, 4 types. And all of these have the same, exactly same underlying scheme. Okay, output is some K times the input. Okay, that's the underlying theme. Okay, where K is called the gain. In this case, this is I. In the case of a current controlled current source, it is represented as beta, so on and so forth. Okay, so that's the idea of dependent current sources, and we'll see how to solve problems with dependent current sources. Okay, and then we went into the idea of Ohm's law. Simply V is I R times I. Okay, the relationship between the voltage and current in a resistance is linear. Voltage developed across the current is proportional to the current flowing through it. Okay. Then we talked about the idea of positive and negative current direction in a resistance. Okay. So I gave you the expression V is IR, and then the opposite, the reciprocal of R is G. That's something we discussed in the last class. Okay. And then we went on to describing the different expressions. Okay. The different expressions that can be used to find the power in terms of conductance, okay, and in terms of resistance as well. Okay, there can be more than one expressions to estimate the power, which is simply V times I. Okay, so all of that we did in the last class. And the other thing that we discussed is the idea of Kirchhoff's current law and Kirchhoff's voltage law. Okay, I told you this class is all about getting a set of tools to solve a circuit. Okay, when I say solving a circuit, I mean finding out all the node voltages and mesh currents, all the node voltages and all the branch currents. Okay. When I say solving for circuit, I'm really the thrust of my effort is to find the values of all V and I. Okay, so along that process, I gave you two tools. One is a passive sign convention that we follow, and the other is Kirchhoff's laws. Kirchhoff's laws, there are two of those, and we are going to see them in action today using problems. Okay, Kirchhoff's current law has to do with nodes. Okay, when I have a node, okay, node is a connection of more than one um, wires. Okay, so Kirchhoff's current law says if you add all the currents at a particular node, that should equal zero. Okay, so there are four nodes in this circuit. We can set up four different equations using those four nodes. So there is a node A, there is node B, there is node C, and node D. And I gave you an example of applying Kirchhoff's law at node D. Okay, at node D. And I gave you some convention. If you're using, if the current is flowing in, call it negative. If the current is going out, call it positive. Okay. I'm going to, in this class, solve a problem. Okay. And in the problem, I'm going to show you a bit more simple approach than having to remember this. Okay. So I'll talk about that. Okay, Kirchhoff's current law simply says at a given node D, for example, if you sum all the currents, they're going to be adding to zero. Kirchhoff's voltage law it deals with closed paths. Okay, paths. If you look at this particular circuit, I can consider the purple path as one closed loop, a closed path. Similarly, I can set up another loop. Any closed path, I can begin with one node and traverse my way all the way back to the same node in a closed path. Okay, begin somewhere and end up in the exact same node. The voltage drop, if you add up all the voltages um, along that path, that sums to zero. Okay, so that's the idea. Some of these things are, I don't want to go more theoretical on this. They're better explained and understood using problems, which is what we are going to do today. Okay, that's the idea of KCL and KVL. We look at some problems. Okay, and then how do you solve for circuits that have dependent current sources? Okay, that is something we are going to look at as well. Okay, so in today's class, it's mostly going to be about problems. Okay, so let me do this. Let me add a page at the end and title it as some example problems. Okay. Okay. So in order to look at some problems, what we do is I'm going to do this. Okay. So if you look on Moodle page, okay, the Moodle page somewhere in here should say Chapter 2 textbook problems, PDF. Okay, so let's start by solving these problems. Problem 2.22. Here is a circuit, and in this circuit, the value of I0 is given to be 2 amperes. And then we are asked to find out I1, current I1. okay? And also the power dissipated in all the resistors, okay? And we want to verify that the power dissipated in each of these resistances is the same as the total power consumed. What happened there? Okay, so let's start by looking at this very simple circuit. Okay, let's see. I'm going to take a screenshot of this and export. Copy that. Okay. Okay, so now there's a, now let me go back to my notes and paste it here. Okay, so here is the problem 2.22. Okay, this value in the problem is given to be 2 amperes. That value is given to be 2 amperes. Okay, and we are expected to solve this problem, solve this circuit. So let us start by doing some simple basic annotations on the problem, on the figure here. So first of all, I'm going to set up some directions. Okay, these are assumptions. And as long as I stick to these assumptions throughout the problem, I'm going to arrive at the correct solution. Okay, so I'm going to assume that the direction are positive and negative. It does not matter. I might as well have set up negative and positive in the opposite fashion. Regardless, I'll be led to the correct solution in the end. Okay, so let me call this I4 because this is I1, I0. I'm going to call this as I2, name this as positive, and assume this as negative terminal, and assume the voltage drop in the same direction as the current flow. So current is flowing from top to bottom in I1, 4 ohm resistance. So I'm going to name the top one as positive and the bottom one as negative down below. Okay, I'm going to call the current flowing in this resistance as I3. Okay, assume a positive there and a negative there. Okay, so what are all the unknowns? I have I0, I1, I2, I3, and I4 are my circuit current variables, of which I know I0. I0 is already given. Okay, I0 is already given. So I have 4 unknowns. So I will need 4 equations to solve them. Okay, to solve for all the unknowns. Okay, let's see by identifying all the nodes first of all. Okay, there are 4 nodes. First node, node B, node C, and node D. Okay, there are 4 nodes, and let me annotate them as node A, node B, node C, node D. Okay, so the first thing I'm going to do is to set up KCL at different nodes. Okay, so I begin by setting up KCL at node A. Okay, so I'm going to, I forgot to call this guy as I source or I total. Okay, I source or I total. So there are 5 unknowns now. So the unknowns are I1, I2, I3, I4, and the total current that is being delivered by the voltage source here. Okay, these are the unknowns. When I solve for all the unknowns, when I have an answer for all of those, then I know I solved the circuit. Okay, questions please, questions so far. So let's begin by applying KCL. Okay, I mentioned there is a convention that we follow about KCL, and I told I was going to give you a simple technique. Okay, the easy way to remember KCL is at, at this particular node A, okay, at node A, look at all the currents that are coming into the node. IS is the current coming into the node. And what is the current flowing out of the node? I2 and I4. Okay, so an easy implementation of KCL is sum all the currents coming into the node and all the currents leaving the node. Okay, as you can see, I4 is leaving the node, I1 is leaving the node, that particular node. So I added them here, I2, sorry. IS is coming in, so I added it on the other side. So that's, now I don't have to worry about signs anymore, positive or negative. I just started out by setting up the current direction in that fashion, and then I stick with that. So let's do this again. Let's apply KCL at node B. Okay, at node B, the current entering is I2, and the current leave, so I2 is the current entering. That should equal all the currents leaving, I3 plus I1. Okay, so that's KCL at node B. Does that make sense? So do you want to apply the KCL at the next node? Any volunteers to do that? KCL at node C. What would be the expression for KCL at node C?
So would it be that I4 plus I3 is equal to the I naught?
Correct. I naught is I4 plus I3. Similarly, KCL at node D simply means IS, that's the current leaving, that should equal I1 plus I0. Correct? So that is I0. This is I1, that's the current entering. IS is the current leaving. Okay, so it appears that there are 6 unknowns: 1, 2, 3, 4, 5, 6, which is not really the case. So if there are 6 unknowns, I need 6 equations. Okay, but I really don't have 6 unknowns because I0 value is given, right? I0 is given to be 2 amperes in the problem. Okay, so there are only really 5 unknowns: I1 through I4 and IS. These are the 5 unknowns. Well, in order to solve for 5 unknowns, I need 5 equations. Okay, but it only seems that we have 4 equations here: equation 1, 2, 3, and 4. Equation 4. There are 4 equations, and that's about all we can squeeze from KCL, because there are 4 nodes. I set up 4 equations using KCL at each of one equation at each of these nodes. So now, in order to set up the 5th equation, I have to, it seems, use something else. I have to use KVL. Okay, I have to use KVL. Okay, let's see how we can use KVL. Okay, we can, so let me do this. KVL, I'm going to use, let's say, this color. KVL around loop. Okay, and there are a bunch of different loops. I could select this loop okay? Or I could select this guy as a loop, or I could select this guy as a loop. Any suggestions on which one you might want to choose?
Would it be more prudent to use the whole loop and then set it to 0?
That is
Does it,
correct. And you're exactly right. And why would you think that that's the case?
to simplify solving for them later, but I don't know. Some
Thank you.
rules.
Yeah. It makes our life simple. You're spot on. Thank you. If you think about it, KVL deals with voltages, right? You're adding up voltages along a particular loop. So you start here. So the typical way to apply a KVL is to start at the lower left, okay? Lower left corner and follow the loop, okay? Follow the loop and reach all the way to the beginning point. So when you're doing that, you're following the different components in there. Okay, so let's see how we can apply KVL over that loop here. Okay, so I'm going to show you the application of KVL here. So we begin at the lower left corner right here and follow. We are looking for voltage sources. There is a voltage source here, right? But it's going from negative to positive, okay, our direction. So I see a negative sign there, so I begin with negative 80 volts, okay, plus the voltage dropped across this resistance is plus, because I see a plus here, okay, plus 80 ohms, sorry, 8 ohms times I4, okay. Then I arrive at this guy. So I'm transitioning through each of these resistances. Now I arrive at this 20 ohm resistance. So I see that it is positive on the top and negative on the bottom because that's the direction the current is flowing. So I have 20 ohms times I naught, which is 2 amperes. And Kirchhoff's voltage law says that all of it should sum to 0. Does that make sense?
So now we can just solve for the I4 with this equation, right?
Correct. So that's exactly the reason why choosing this bigger outer loop makes sense, because I know just about everything else in here except I4. Okay, therefore I can simply solve for I4 in this loop. Okay, so by arriving at I4, let's see I4. What's the value of I4 from here then? 8 times I4 should be 40, and I4 is 5 amperes. Could somebody double check me, please?
Yeah, that's what I got.
Okay, I4 now is 5 amperes. So that's 5 amperes coming in. So I have a solution here for I4. Okay, I4 is 5 amperes. What next? What next? How can I use this additional piece of information to solve for something else that I don't know?
You could solve for I3 on node C now that we have I4 and I naught.
Thank you. So that's equation 3. Now that I have I naught and I4, it should be rather straightforward to see I3. What's the value of I3 then? I4 is 5 amperes. Sorry, that's 5 amperes. And I naught is 3 amperes. So I3 should be -2. I3 is -2 amperes, right? Or -3, sorry. So this is 5.
Yes, correct. Sorry, I had my mic muted. I didn't realize.
Okay, this is 5, this is 2. So I3 should be -3. All right, I3 should be -3. Thank you. So now we are slowly getting each of these pieces of information. I3 is -2 amperes, -3 amperes. So you see, something interesting happened here. The reason that I ended up with a negative value here is because I assumed the current to be flowing in this direction. Okay, so what this result -3 is telling me is, well, no worries that you assume the direction of current to be in that fashion. I'm just going to throw out a negative number. So the current is really flowing in this direction, and its value is 3. But it doesn't hurt to think of the same current as flowing in the opposite direction with a negative magnitude. Okay, that is what the negative result here signifies, and I am going to stick to that. I'm not going to change that now. I'm still going to stick with that direction of current. Okay, now let's see. Now I have I3 and I4. What else can I do? It seems that I can apply, I don't know, let's apply KVL around this loop here. Okay, because once you apply KVL around that loop, you will notice that you have the voltage drop information here, and you have the voltage drop information here. So this is the only thing that is left to find out. So let's find that out. Okay, so let's apply the KVL over there. Okay, KVL around the blue loop. Okay, trying my best to keep everything in one screen. Okay, so KVL around loop. We'll call this loop beta. Okay, loop beta. Okay, like I mentioned, how do you begin KVL? You begin with the bottom left corner, lower left corner right here, and you follow a clockwise motion. Okay, so let's do that. The first element that I see is this 4 ohm resistance, and pay attention to the direction here, negative and positive. So I'm going to see a negative I1 times 4 ohms. Okay, and here there is positive and negative. So I'm going to call this as positive I3 times 4 ohms. Okay, plus there is a positive negative I0, positive I0 times 20, and all of that should sum to 0. Okay, so here is the expression. Does that make sense? So it simply followed all the elements in this loop. Okay, and then carefully annotated the positive and negative directions. Okay, so negative 4I1 plus I3 is negative 3 amperes times 4 ohms plus I0 is 2 amperes times 20 ohms. That is 0. And it should give us a value for I1. What is the value for I1?
I believe it's 7 amperes.
7 amperes is correct. Okay, I1 comes out to be 7 amperes. So let's see, this guy is 7 amperes. Thank you. Now we only have two unknowns, I2 and IS. Okay, I2 and IS. Okay, let's see if I can make another copy of the paste image. There you go. Okay, and let's duplicate what we already know here. Copy that. Okay, so this is all the information that we just found out. All right. Okay. Now, what would be the next step then? So I have this value. I have the value of I4.
We could find I source now that we have
I
I1.
source. Yes. Sorry, go ahead.
So you would just add I1 and I naught, and you'll have 9 amperes for I source.
I could add I1 and I naught. And that should give me a value of I source equals to 9 amperes. Thank you. What's the value of I2 that I saw? I don't have a value for I2 yet. Okay. I saw this guy to be plus minus negative 3 amperes. And I found out I1 to be 7 amperes. 7 amperes. And this guy I source is 9 amperes. So I total is 9 amperes. So what's the only unknown here? The only unknown is I2. And I can find out the value of I2 by making the observation that, well, look at this node A equation. This guy, I source. Copy that. So from the KVL that I already established, okay, I know I source should add up to I2 and I4. Therefore, I should be able to estimate the value of, calculate the value of I2 as well. Okay, that comes out to be 4 amperes because I know the value of this guy to be 9 and I know the value of I4 to be 5, which is, this is I4 here, right? Questions, please. Questions so far. So this is 4 amperes. Okay.
So now that we know the currents across each component, are we going to find the voltage across each component?
We could do that. It's just a product of resistance and the current. Or the problem goes on to ask you to find the power drop in each of these resistances. So what you could do is you could do R times I, which is V, and multiply that by I. Okay. So simply, or you could simply do I squared R to give the value of power. Okay. But once the value of I is known and all the resistances are known, you could find out V. But you know, if the problem doesn't ask for it, you don't have to. If the problem does ask you to find the power dissipation in each of these resistances. Okay. All right. So that's the next step of the problem, which I leave as an exercise for you. The second step of the problem is that you do power estimation, the power drop in each of these resistances, power consumed. Then there's a third part to it. Okay, what you want to do is add up the power in each of these resistances. Add up the power in 13 ohm resistance, power dropped in 4 ohm resistance. There's another 4 ohm resistance, and add to that the power dropped in 8 ohm resistance. Then you compare that to the power delivered by the source, which is V source times I source. Okay, V source is 80 and I source is 9. So if you add up all the power dropped, absorbed by these resistances, that should add up to 720 watts. Okay, and which is what you will see for these currents. And that will be proof positive that you solved the problem correctly. Okay, because you're looking at the total power delivered by the power source, and you're verifying that it's dropped completely through the rest of the resistances. Does that make sense? Okay.
Yes, sir, it does.
Okay. Let's solve another problem then. Okay.
Oh,
We
can you
solve
stop?
another problem.
Can you hold right there,
Sorry?
Professor? Go back up above
Yes.
just a little more.
Okay.
I want to see the that's it, the KVL around loop B. Thank you.
Okay. KVL around loop B. Okay.
Perfect. Thank you.
Okay. And all of these notes is going to be available, is already available on Google Drive. So you see the backing up symbol at the bottom left of my screen. It just finished backing up. It means it's on Google Drive already now. So let's solve another problem. Let's solve this problem, problem number 2.23. Okay, find the voltage or the voltage across this resistance. 22.5 ohm resistance is given to be 90 volts in this circuit. Positive at the upper terminal and negative at the lower terminal. So find the power dissipated in each resistance. So he's really asking us to solve for this because we have to find the current through each of these branches. Find the power supplied by the 240 volt ideal voltage source. And when we compare the power supplied by this guy and the power dissipated in each of these resistances, they should add to the same value. Okay, so let's begin that. Okay, copy this. Done.
Professor, when we're talking about the power dissipated by the resistors here, we are talking about the heat as well, right? Like the heat that is going to come off.
Correct.
How do we?
That is correct.
Is there a direct, not equation, but relationship between the dissipation and the heat? Like you can just express it as a temperature?
Not a straightforward relationship. We just know that the greater the resistance, okay, the greater the power dissipated, the greater the temperature. But there must be there must be surely a relationship between them, just that I'm not familiar with that. There is one quick way to find the power is to do simply V times I though. Okay, the greater the dissipated power, the higher the temperature. Okay, so I'm not aware of the relationship between the two. If you think about the power dissipated, I'll give you a real world example. Okay, if you take your sub micrometer, really advanced technologies in the nanometer, 10 nanometer range, or these are the integrated circuits that are fabricated in the sub nanometer, 3 nanometer range technology, that is, or 5 nanometer range, really small transistor sizes. Okay, one of the big problems of scaling down the transistor sizes is that and increasing the activity factor. Okay, power consumed can be a function of half C VDD squared times F. Okay, so if we increase times alpha, the activity factor, if I'm switching capacitance on and off too fast, that's going to consume a lot of power and it generates a lot of heat. And then that's one of the prevailing problems that a lot of people are paying careful attention to in terms of reducing the total heat, power consumed, and dissipating the heat through proper heat sinks, good design, so on and so forth. Okay, but I know for a fact that in some of these pushed technologies, dissipation, heat dissipation is an extremely big problem. Okay, so that's the idea. Now let's go about solving the next problem. Problem P23. That's a good question. Thank you. Okay, problem number 2.23. Okay, so let's see. Let's make some observations here. And the first thing we do, as always, is to set up arbitrary directions. Okay, so let me call this as I total. Okay, or I source, I total. Okay, and I'm going to call this as I1. This guy was given, right? I1. Oops. This guy is kind of given, I1, because the voltage drop across that is given, positive up there and negative down below. Okay, I'm going to assume the direction for the current in this resistance to be this guy, and I'm going to call this I2. Similarly, I'm going to call this as I3. That's the current flowing in this resistance, I3. Okay, and then positive, negative here, and positive, negative over here. I'll call this as I4. This guy as I5. Okay, so there are a bunch of unknowns: I1, I2, I3, I4, I5, and I total are the unknowns, right? Well, some of them are already known. I1 is known. I know I1 because I1 is given to be the voltage 90 is given. If I divide that by 22.5, which is the resistance, I should get a value for I1. So this comes out to be 4 amperes. Okay, I1 is 4 amperes. Okay, now it seems that there are 1, 2, 3, 4, 5 unknowns. So I would need 4 equations. Okay, so let's see. I can use 1, 2, 3, 4 nodes to set up 4 equations, KCL, and one more, a mesh or KVL to set up the 5th equation. So there are 5 unknowns. I need 5 equations. Okay, so do you have a suggestion on how to begin the problem? So let me call these as nodes. Let me name these nodes as node A, okay, then node B, node C, and node D. Okay, there is more than one ways to do this problem, a bunch of different ways. Okay, a bunch of different ways to do this problem, but I will begin. So this guy is 4 amperes. Okay, so I will begin by applying KCL at node A. KCL at node A. Okay, If you look at node A, which is this guy, there is one current coming in, which is I total, and two currents leaving out, I1 and I5. Okay, so sure, that's one equation for me. I total current coming in equals to I1 plus I5, right? I could do the exact same thing at node B as well. KCL at node B. Now, how would that equation look?
It'd be I2 equals I4 plus I1.
Correct. I2 equals I4 plus I1, which is 4 amperes, because I just found out that I1 is 4 amperes. Right? Nice. Let's do the next one. KCL at node C. Okay, KCL at node C.
I would
So
think
that,
it I total equals I3 plus I2.
thank you. Okay, now KCL at node D.
I5 equals I3 plus I4.
I5 equals I3 plus I4. So that's 4 equations right there. 1, 2, 3, 4. Okay. Now what? What do you want to do for the next problem, next step?
We could do a loop around the complete outer perimeter, since that would give us 2 knowns and then 1 unknown.
Thank you. Isn't that a very astute observation? Did you mean this loop?
Yes.
Perimeter. Okay. Okay. I'm going to call this as loop alpha. Okay. KVL around loop alpha. Okay. It is based on the observation that I already know this current to be 4 amperes. So I know the voltage drop here. Well, I already know this guy as well, the voltage drop here. So there's only one unknown in there. That's a very sharp observation. So I start at the lower left, okay, and follow a clockwise path. I see a negative 240 volts to begin with, plus, then I come to this resistance, okay. So there is a 22.5. Well, it's already given to be 90 volts, right? So I don't even have to do the math. It's given to be 90 volts in the problem. 90 volts plus. So now I follow the path through this resistance. So which is 15 times. Let me make some room here. So in this resistance, 15 ohm resistance, the voltage drop is 15 times I2. And according to KVL, that should all add to 0. Okay, all of that should add to 0, which would give me a value for I2. What's the value that you find for I2?
I believe it's 10.
Perfect, thank you. So I2 is 10 amperes. Okay, I2 is 10 amperes. What else can we do now?
We can solve for I4 at node B, because we have I2 now.
Okay, so what you're saying is I have I2 here and I have, perfect. So I can find out the value of I4 to be 6 amperes.
Yes.
Okay, perfect. Now what? So this guy is 6 amperes. This is known, right? I4 is 6 amperes. And this is known, I1 is 4 amperes. So that part is known. Okay. So what I'm going to do is probably apply KCL one more. Yeah, go ahead.
I'm sorry. Could we do a KVL loop around the diamond shape with all the resistors?
Like so?
Yes.
Sure, but what are the unknowns there? Do we know I3? Well, we don't know I3 and we don't know I5 either. So that's too many unknowns for me. We could do that. We'll just end up with another equation. How about this?
So just half of it then?
Half of it. That's a close path too, right? So I know two of those, I5, I know I4 and I1. Then I should be able to calculate I5. So let's do that. So let me color code this KVL around loop beta. Okay, I set up more equations than I need, but it is as well because it gives me a very good practice. So let's see. I start with the lower left part of the loop, okay, and follow a clockwise path like so. Okay, that's the path I'm going to follow. So who can help me begin setting up the equation here?
I believe you would have 4I5 plus 90.
4 ohms times, don't forget the negative I5, because my loop is going in this direction and I encountered a negative there. So the current I5 was flowing in this direction, right? So I have to account for that. Now, correct. Then this guy, right? Plus,
Right. So then plus the 90.
plus 90.
And then minus 5I4 equal to 0.
Thank you. So that should give me a value for I5. What value does it come out to be?
Is it the 15?
That's what I
15
got as well.
amperes is correct. 15 amperes is correct. So I5 is 15 amperes. Okay, I like the interaction in the class. Thank you for participating. That's cool. Now, what's my next step? I should be able to calculate I total, right? Because I have I5, sure enough, and I do have I1. So if you look at this guy, oops, if you look at that, if you look at this current I total, that's the sum of these two. So using the equation that I already set up for KCL at node A, I should be able to estimate, I should be able to calculate the value of I total.
So then I
To
total would
be,
just
go ahead.
So I total would just be 19.
19 amperes. Thank you. So it seems I3 is the only unknown here. Okay, I filled in all the rest of the blanks, and there's only one thing that I still need to solve.
Use
I3.
the KCL at node C, since IT is equal to I3 plus I2.
Thank you. I could use this expression here to calculate I3. Get this equation, which gives me a value of 9 amperes. That's what I have here. Somebody could double check, that'd be perfect.
Yes, sir. That is correct.
Perfect. So voila, what we have done here is we arrived at the current values. These are humongous values. 19 amperes, 15 amperes. These are extremely large values. Okay, these are extremely large values, only there for instruction purposes. I don't think it's really practical. Okay, now, so that's just one small part of the problem. There are two other aspects of the problem, right? Finding the power dissipation in each of these resistances. Well, all you have to do is I squared times R, or V times I. Okay, I leave that as an exercise. Then the third part is add up all the power drops and make sure that equals 240 times I total, which is 15 amperes, which is 19 amperes here. Okay, so the power delivered by this guy should equal the power dissipated in each of these, equal the total power dissipated in the sum of all the resistances. All right, questions, please. All right. So we look at another problem then, third problem. So what all we are doing is simply following some basic conventions, some passive sign conventions, setting up node equations, using KCL, setting up equations around a loop using KVL. Okay, let's do one more problem. The problem I want to do is, let's see, I'm not sure I have it. Problem number 2.35. Let's see. Problem number 2.35. Before that, we can look at this guy. Why don't we look at this problem? Okay, let's copy that. Then we can come back to solve problem 2.35. Okay, this is a little different problem. Take a minute to see what's going on here. What is different about this problem?
It has a dependent current source.
It does have a dependent current source. So in that sense, it's a slightly different problem. Let's see if we can solve this guy using some of the techniques that we already learned. Okay. Okay. So the question, I think, let me read the question so I feel that I'm working not in vacuum, but so find the current and voltages, find all the currents and voltages in the following circuit. Okay, that's what we are interested in finding. Okay. Okay, so let's see. The problem is to find I delta. Okay, find I0. Once I have I delta, I should have the value for 5 times I delta, which is this guy. Okay, and I'm also interested in finding all the voltages V0, which should be straightforward. And I'm going to call this as V delta as well. V delta is the voltage drop from here to here. V delta. Okay, and we are expected to find all of these. It's not, it's a simple problem compared to what we have already done. Okay, it's a simple problem compared to what we did, but it does have a dependent current source, so that it's better to solve one or two of those problems. Okay, so let's start by looking at the nodes. Okay, let's look at the nodes. Node B, node C. There are two nodes. Okay, let's start by setting up the node equations. KCL at node B. Okay, when I look at the KCL at node B, the amount of current coming in here is 5 delta, 5 I delta. Okay, so I0, that's the current leaving, equals to sum of I delta plus 5 times I delta. So I have an equation I naught is 6 times I delta. That is given by KCL at node B. Okay, let's do another equation, KCL at node C. Okay, but instead of doing that, that may be a bit redundant. What we will do is we will try to set up a KVL around some loop that looks like so. Okay, let's look at this loop here. Okay, let's look at that loop. We'll set up KCL around that loop. KCL around loop. And I'm going to just name it alpha, loop alpha. Okay, just so it's easy for me to differentiate. Again, as always, I begin at the lower left, okay, and follow a clockwise path. The first thing I encounter is negative 500 volts, okay, followed by positive 5 ohm times I delta plus 20 ohms times I naught. Okay, all of that should sum to 0. Okay, negative 500 volts plus 5 ohms times I delta plus 20 ohms times I naught equals to 0. So that should tell, yeah.
I just want to clarify, this is the KVL, right? Around loop alpha?
Correct.
Okay, just making sure.
Exactly. So there are 3 components to this KVL. The first part is the voltage across that guy, which is shown here. The next part is the voltage drop across this resistance, which is 5 ohms times I delta. The third part is the voltage dropped across this guy, 20 ohm resistance, which is 20 times the current. The sum of all of those along this path, this loop, should equal 0. Able to see that better now? Okay. So 500 equals 5 times I delta plus 20 times. In place of I naught, I'm going to simply replace it with 6 times I delta. So that's 6 times I delta. Okay, so I should get a value for I delta to be 4 amperes. Okay, once I have a value for I delta, I should be able to get a value for I naught, which is 20 amperes. So I delta is 4 amperes. Somebody could double check me on that. I naught is 20 amperes.
That's
Oops.
correct. That's what I got as well.
Okay, I naught. How about I naught? Is that 24? It's supposed to be 24, I thought. This is 24. And 5 times I delta is 20 amperes. Okay, once we have that, I should be able to estimate the value. I should be able to calculate the value for V naught, which is simply 20 times I naught. And I should be able to calculate all the voltages. Does that make sense? Okay. Questions, please. Questions so far. Okay. Let's see if we can solve one more problem. Okay. Let's see if we can solve one more problem. And that's problem 235. I'm just trying to find the problem. Okay. Let's see. Problem 2.35. I can't find it, so I'm simply going to write it out. Problem 2.35. Okay. Problem 2.35 is a couple of one dependent source. Okay. There's a 12 kilo ohm resistance in here. There is 8 kilo ohm resistance in here, plus minus 200 volts. There's another okay. There's a dependent current source here, which is V delta over 200. Okay. Then there is this resistance. It's a slightly different problem here we have. Okay. Then there is another resistance, 3 kilo ohms. And I'll give you the values shortly. So this is 9 kilo ohms. And this guy is 3 kilo ohms. Okay. So we had expected to find the currents and we had expected to solve for the different currents and voltages in this circuit. Okay. What observations do we have at this point? How is it different? What differences do you see it from what we have already seen? It's different in more than one ways.
It's not a complete closed loop.
It's not a complete closed loop. So the current that is going in has no way to come out through this path. It's not a complete closed path. So the assumption I can make about this circuit is that the current going in here is 0. Okay, the current flowing through that branch, I know, because it's not a closed path, any current flowing in there has no way to come out. So I can call this 0. I can assume that to be 0. Okay. The second difference is that there's a dependent current source. Well, what I have not shown, there's a missing piece of information. This current source, whose value is V delta over 200, its value is V delta over 200. What is that V delta? That's this guy. That's this guy is V delta. Okay, that's the idea of V delta. Now, let's see if I can start the problem by setting up some currents and some directions. Okay, so I'm going to call this I total. Okay, I'll name this as plus, this minus. I'm going to call this as I3. Okay, this one, this is plus on the top and negative on the bottom. This is going to be I3 as well, right? See, that's the same current flowing here. There's no branch to split the current. Okay, that's I3. Okay, then I'm going to call this as IX. The current going in here is IX. Okay, which is given to be, IX is given to be V delta over 200. Okay, this guy is a positive sign over here and a negative sign over here. That's going to be I1. And this guy is I2, plus and minus. Okay, positive and negative I minus. So let's set up some nodes here. Let me call that node A. Let me call this node B. And then maybe there's a node here, node C. So it's node A, node B, and node C. Okay, A, B, and C. Very well. Let's see by setting up KCL at node A. KCL at node A is I total, that's the current leaving that node, equals I3 plus I0, which is 0, right? So that's one equation. So that's a trivial equation. KCL at node B. I have the current leaving is I0, which is 0. That is equals to the sum of the currents entering the branch, entering the node, Ix plus I1 plus I2. So once I make the simplification that the current flowing into that single lone wire is 0, the rest of the circuit is pretty straightforward. Okay, and I can set up a KCL at node C. What's the expression for KCL at node C? The same thing. Let's see, something's wrong. This is supposed to be I2, isn't it? Okay, which is exactly the same that we will see at, so Ix, the current leaving that node plus I1 plus I2, they should sum to 0. Okay, so both of these are actually only one equation, the exact same idea. Okay, so it seems that I need more equations. There is 1, 2, and 3, the unknowns. Okay, so let's see if I can use KVL. Okay, I'm going to define a loop using this color and that thickness, this guy. Okay, loop alpha. So why don't you set up the KVL around loop alpha? and give me the expression for that.
So would it be negative 200? And then 8I3 plus
8 kilo times I3 plus
12KI3. And that will equal 0.
So that should give me a value for what value for I3?
I believe it's 0.01.
Which is 10 milliamperes. Thank you. So that's normal to say. That's a bit more reasonable number as opposed to 19 amperes. Okay, 10 in the previous problem it was in 19 amperes because the resistances were small in ohms. This is a bit more realistic number. Kilo ohms resistance means milliohms, milliamperes, roughly for tens of voltages or hundreds of voltages. Okay, mega ohm are set up usually with microampere, something like that. Okay, so this is a bit more reasonable, realistic, milliamperes. Okay, so that's one thing. So we are expected, the problem asks us to find V delta. Okay, that is what is explicitly asked in the problem, which should be easy to do, which is 12 kilo ohms times I3, which is 10 milliamperes, which happens to be 120 volts. Okay, 120 volts. So V delta equals to 120 volts. Okay, what else can we do here then? So I know the value in V delta, the voltage. Once I know the value in V delta, notice the magic of a dependent current source. So whatever value is set up here, and we know that's the 120 volts here, the current here is going to be dependent on that, and that's at the heart of the dependent current source. V delta, if it is 200 here volts, the current here, Ix, is going to be dependent on that 200 over 200. So that's the idea. Okay, the idea is that V delta is this guy. Okay, so once we know V delta, I should be able to calculate Ix, which is V delta over 200, which comes out to be 120 over 200 or 0.6. This happens to be 0.6 amperes. Okay, that's I delta, Ix, I'm sorry. Okay, once we know Ix, I should be able to see that I can plug this back in as 0.6 here. Okay, and then see that the sum of I1 and I2 is 0.6. Okay, negative 0.6. So let me see what else I can do. Okay, it seems I found out the value of I total, which is same as I3, to be what value is that again? 10 milliamperes. So I found the value of Ix to be 0.6 amperes. Now what I do is, what I need is I1. What's the value of I1? What's the value of I2? Okay, so in order to do that, I can modify this equation to say I1 plus I2 is negative 0.6, because I got a value of 0.6 here. So that much I can use. So in order to break that equation, what I'm going to do is to set up a loop equation around this guy. Okay, let's set up a loop equation around loop beta. Okay, when you do the KVL around loop beta, okay, what you have is you start with the bottom left, lower left, and then follow a clockwise pattern. So what you do is negative 9 kilo ohm times I1 plus I2 times 3 kilo ohms is 0. Or in other words, is simply one is equals to the other. Okay, 9 kilo ohms times I1 equals to. So you have an expression that gives you KVL around beta. Okay, I have a couple of minutes, so why don't I do this properly? Negative 9 kilo ohms times I1. That's beginning at the lower left corner, going through the 9 kilo ohm resistance, plus I2 times 3 kilo ohm. That should sum to 0. Okay, so I have I2 to be 3 times I1. Okay, that is coming out of this equation here. Okay, I2 is 3 times I1. So if I take these two equations, this guy and the one below, if I take these two equations together, I should be able to solve for I1 and I2. Okay, if you do that, I1 is going to come out to negative 0.15 amperes, and I2 is going to come out to negative 0.45 amperes. Okay, let me write it out here. So I1 is negative 0.15 amperes, negative 0.45 amperes. Okay, so we set out to find all the voltages and currents, and here we are. We have all the currents, and I leave it as an exercise for you to find the voltages, power supplies, and anything else in the problem. Does that make sense? Okay, so the only different observation here is based on the fact that even though there is a connection here down below, it's as good as not being there, because there is no path for the charge to flow back. Okay, so that's just independent circuits. The only connection, now why don't I leave it as a question to you? If I break this connection, can you consider them, because it's as good as broken, right? Can you still consider them as connected circuits? If yes, why? Or put it another way, what is the real connection? Because this is a fake connection. There's no current flowing in there. It's as good as not being there. So are these two different circuits totally altogether, or are they somehow dependent on one another, or what's the connection between these two? What connects these two seemingly separate circuits?
The dependent current source being connected
It's the
to delta
dependent
V.
current source. Correct. That's exactly right. So the dependent current source looks at the voltage V delta here, okay? And based off of that, its current value is changing. So that's the real hidden connection, okay? This sometimes, many times, you can think of this as a MOSFET, okay? Where the voltage between two terminals is setting the current between some other terminal, which is not directly connected. Okay, so you're right. It's the dependent current source that is tying these two separate branches together. Okay, questions, please. Questions, comments, concerns.
So would that make it, even though there's no wires connecting, it would still be considered one circuit then?
Yes, it's still one circuit, and what ties these two different parts of the circuit together is the dependent current source. Okay, this value is dependent on the voltage here, and that's a hidden connection, not shown. Okay.
Okay, thank you.
Other questions, please. I'm pleased with the level of engagement, discussion, and feedback that you're giving here. I only ask that you keep this up throughout this semester, and then I encourage more of you, more um, um, students to take part in the discussion. Okay. Any last questions, comments, concerns? So all of this is going to be available on Google Drive in a couple of minutes when the backup completes, and you should have access to all the notes. Okay, so I'll see you folks back on Monday then.